This interactive figure, we have a current carrying wire, and the current is actually shut off right now because the switch is closed. And that current wire is actually running through a magnet, and so there is a magnetic field that is directed from the north end of the magnet over towards the south in between this horseshoe magnet. So we can look at what happens when we actually turn the switch on. And so if we turn the switch on, oops, I turned it off again. There we go. I have current that is running through this wire. I have the positive end here. Current is running through this wire, and as it passes through the magnet, the current wire is actually deflected. And in this particular case, it's deflected down according to the direction of the current. Now I can adjust the voltage of the battery, and as I adjust the voltage of the battery, that will also change the current. So let's see what happens as I adjust the voltage of the battery, increasing the current. As I do that, the deflection of this current carrying wire is greater and the force on that wire is greater. So this arrow here is representing the direction of the force. So as I look at this picture, I have a magnetic field that's going from north to south. I have current that's going through the wire, sort of through that magnet, and then I have a deflection downward. So the direction of the force is actually perpendicular to the direction of the magnetic field, and it's also perpendicular to the direction of the current going through the wire. So let's see what happens as I decrease the voltage. So watch the wire up here, and we can see the force. As I decrease the voltage, I'm decreasing the current in the wire, and eventually when I reach 0 volts or 0 current, there is no longer a force acting on the wire. So there's 0 force if there's no current running through there. I'm going to go ahead and turn the switch off now, and I'm going to put the voltage back to 12 volts as I had it before. But now I'm going to change the current direction. So now the current is going to be going to the left, so the polarity of this battery has switched and the current will run through in the opposite direction. And let's see what happens when I turn the current on by flipping the switch. I notice that the deflection on that current carrying wire is now upward, so the direction of the force is upward. So when the current switched direction, the direction of the force on that wire also switched direction. And then again, as I adjust the voltage, right, that increases the current, and therefore the force also increases. So it turns out that the force on a current carrying wire depends both on the direction of the current and also the amount of current that's going through the wire. It turns out, and we can't see this in the simulation, but the current carrying wire is going to experience the greatest deflection when the wire and the magnetic field are perpendicular to one another, which is exactly the case here. The magnetic field is going between the north and the south of this horseshoe magnet, and the current carrying wire is going through that, so they are perpendicular to one another, and that's when the greatest force actually occurs. So if this current carrying wire was actually going through at an angle, a slightly different angle, then the force would not be as great. And in fact, the wire experiences the least amount of force, and the force when they are parallel to one another, and that's actually 0. So if the wire was lined up so that it was going directly from north to south in here, then the force would be 0. So the greatest amount of force on a current carrying wire is when the magnetic field and the wire are perpendicular, and it's the least when they are parallel to one another.